Okay, hello everybody. I'm Janmajaya, and I'm from Phantom Zone. Today I'll be talking about something quite special, the encrypted computer. So you might wonder what the encrypted computer is, right? Well, the encrypted computer is sort of is a black box. What it does is that it takes encrypted programs. So you write a program on your laptop, you write it, and then you encrypt it locally on your device. And then you send it to this computer, and this computer would execute your program without learning anything about your program. What it can do in addition to that is this computer can also take encrypted inputs from someone else, and then can run the encrypted program on the encrypted inputs and give you the output. And it guarantees that no one can learn anything about the program, no one can look inside its memory, no one can learn anything from the execution trace. So everything remains encrypted. The only thing that you learn is the outputs. Now, okay, so for the rest of my talk, I'm going to sort of ignore a very important question, like why is this encrypted computer useful, which is important in another respect, and probably if you were at Jordy's talk, you would realize why it is important. What I'm going to focus on is how do we go about building this encrypted computer? Like how do we sort of get to the point where this is practical? So the first question that comes to mind when you want to build the encrypted computer is, essentially if you realize what you want to do is that you want to compute on encrypted programs. Like you want to implement a virtual machine on encrypted programs. How do you do that? Then the question reduces to how do you compute on encrypted information? How do you compute on encrypted data? And if you go around, if you go to your neighborhood and ask a cryptographer over there or someone who's familiar with cryptography, how do you compute on encrypted data? Their answer would be straightforward, like just use fully homomorphic encryption and the thing works. So what's fully homomorphic encryption? Basically, like fully homomorphic encryption is a very simple idea. What you can do as a user is that you have a private information. You are in a dilemma. What you want to do is that you have private information, but you want someone else to compute on the private information and give you something else. Using FHE, you have a FHE secret key. You encrypt your private information using your FHE secret key, and you get an FHE ciphertext. No one can learn your private information, but you can still give your FHE ciphertext to someone else. They can compute on your FHE ciphertext, meaning that they're actually computing on a private data. And then produce a FHE output. And then you get the output FHE ciphertext, and you decrypt using your secret, and you can learn the function evaluated on your private input. Given the fact, cool, so what do? We tried building this encrypted computer, and we in fact built it using FHE. We, for some reason, call it Phantom. So we prototyped this and what we did is that we took RISC-V virtual machine, like RISC-V virtual machine spec, and then we implemented the RISC-V virtual machine spec using FHE circuits. So we simply wrote the entire spec in FHE circuits, and that's how you get a RISC-V virtual machine that is encrypted. So we prototyped it out. The full implementation is not ready yet. It is still under development. The VM does exactly what you want to do. It takes encrypted RISC-V binaries that you can write, like as a developer, you write in Rust. It compiles down to RISC-V. You encrypt locally on your device. You get encrypted RISC-V binaries. And the VM, you send to the VM, and the VM would execute it. As simple as that. The problem is that it's pretty slow. It's like 2 cycles a second. Well, at the moment, it's not still 2 cycles a second. I think it has increased until like 2.5, something like that. But the improvements are happening. I think that with advancements in FHE and some engineering advancements and putting a lot of investments into engineering stuff, and if you allocate resources to improving the speed of the RISC-V VM, we would be able to make it a lot faster. Like, this is just the first prototype that we have, and it gradually will be making it a lot faster. And today's focus would not be this. Today's focus would be something that FHE itself cannot be solved. But it is very important to, but these problems are more important to build the trustless computer, like the trustless encrypted computer. And why is that the case? Because FHE has a problem. The virtual machine that we built using a fully homomorphic encryption needs someone to hold the secret key. The best that you can do today is that you can take the secret key and shard it among a threshold committee. So you have like multiple servers that hold some shard of the secret key, and as long as these servers don't collude, like they don't come together and sort of play against you, as long as they don't collude, everything is secure. But the moment they collude, things sort of like break. So that's the best we can do at the moment with FHE. And we need to get around this problem. What are the missing parts? Well, there are two more things that are necessary. The first one is publicly verifiable FHE. I'll get to that. And the second one is practical obfuscation. The reason that I mentioned practical obfuscation is because there exist schemes for obfuscation, but they're not practical. And for the details that I'll mention later, practical obfuscation only for something called conditional decryptor suffices, and I'll get into the details what that means. So what is publicly verifiable FHE? Well, it's pretty simple. You modify the FHE scheme so that instead of just executing on encrypted data, it also produces a proof of execution. It also produces a proof that I've executed the FHE circuit correctly. Why do we need this? Well, one instance of this could be that we implement the entire RISC-V VM that we implement at the moment using normal FHE. We implement it using publicly verifiable FHE so that the virtual machine outputs the encrypted output, which is what we need. In addition to that, it outputs a proof of execution, sort of claiming that I executed the program correctly, so you do not have to trust the machine to do it. Like, you can verify it yourself. What is obfuscation? Well, using a practical obfuscation scheme, you can take a program P, like any program that you want, and you can transform it, like obfuscate it, and get an obfuscated program. And you can give this obfuscated program to anyone else. They can, execute this program on any input, produce some output. Think of it as like an API to the program. But what they cannot do is that they cannot learn the exact instructions of the program. They cannot learn anything about the implementation details of the program. One instance of this could be that you take your, you sort of encrypt your program that signs using a secret key. You sort of obfuscate it and send it to someone else. Now, anyone can produce signatures on your behalf, but they can never learn your secret key if you obfuscate it. Okay? So why is publicly verifiable FHE and conditional decryptor relevant? Well, what you can do is that you can first have the RISC-V implemented with publicly verifiable FHE, and it produces the encrypted output, and in addition to that, it produces a proof of execution. And then you can write a program called conditional decryptor. This conditional decryptor hard-codes the secret key of the FHE, secret of the FHE, which at the moment is sort of sharded among threshold committee. It hard-codes the secret key, and then it verifies the proof, and then and if the proof is valid, and it decrypts if and only if the proof is valid. Otherwise, it rejects. In this case, you're trusting the obfuscation scheme. You're not trusting the threshold committee anymore. Now, you might be concerned, like, how do you hardcode the secret? Well, the way we do that is that we sort of like perform a trusted setup that we do at the moment for zero-knowledge proofs. We perform a trusted setup, obfuscate this conditional decryptor with the secret key inside it, and that's it. Okay, so what is the state of publicly verifiable FHE like? How practical is it? At the moment, you have to pay roughly like 1.5 to 2 orders of magnitude cost over normal FHE schemes. But as all of us are aware, cryptographic proof systems and FHE both are like both are advancing rapidly. And I don't see any blockers in sort of like bringing down the cost of publicly verifiable FHE to something that is more practical and that we can use widely. You would obviously have some cost over normal FHE for publicly verifiable FHE, but I think it would be somewhat minute. I don't think that it is that a big of a problem. So I'm not going to talk about this further because the other problem that I mentioned, obfuscation, is in a much more depressing state. What is the state of obfuscation? Well, there are multiple approaches. There's no secure and practical scheme. There's a secure scheme, so we know that obfuscation exists. Like we know that it is true, but there's no practical construction for it. I'm only going to cover 2 approaches, and my intention with covering these 2 approaches would be to first sort of give you an intuition of what that is, in addition to tell you about the problems and sort of give you a flavor of what the problems look like. The 2 approaches that I'll be covering are local mixing and obfuscation of matrix branching programs. Local mixing is fast, it's practical, but it's not secure. We don't know whether it's secure. Its security is based on things that we don't understand well enough, so we cannot say anything about the security. And the obfuscation of matrix branching programs is probably secure, but it's very impractical at the moment. Okay, so what is local mixing? Well, local mixing says that, instead of obfuscating Boolean gates, I'm going to sort of change the model of computation. I'm going to obfuscate something called reversible circuits. And you can think of reversible circuits as a collection of bit strings, like collection of wires. And you put in gates one after the other, and each gate is itself reversible. What do you mean by reversible? Well, a reversible gate is something that if you put in the input, you get the output. You can always you can always go from output to the input as well. For instance, AND gate is not reversible, because AND gates, if you perform an AND, it loses information. But if you can express an AND gate in a reversible manner by something like this, where you sort of have A, B, and 0, these are the bit string, you have this reversible AND gate that sort of takes A and B and XORs the third wire. So you store the information of A and B into the third wire. And you get output as A and B. If you look closely over here, you can definitely go from this to this back by just going the other way around. So you take these gates, many of them together, and that's how you construct the reversible circuit. So the local mixing approach sort of says that instead of obfuscating Boolean circuits, let's just obfuscate reversible circuits. Now, the reason for that is somewhat more involved, but it somewhat follows from the fact that reversible circuits are easier to understand and has less surface area of attacks. And it has some nice mathematical properties that you can play around with to come up with proofs or something like that. Okay, so the first step in obfuscation of local mixing, the first step in local mixing approach, is to obfuscate a random reversible circuit, like a randomly sample. You just sample a reversible circuit of nowhere, and you have to obfuscate that. You can think of it as, if you're familiar with cryptography, as you need to come up with an obfuscation scheme that obfuscates a random functionality. That's the first goal of local mixing. So for now, we'll be only concerned with how to obfuscate a random reversible circuit. And there are 2 steps to do that. And I call these 2 steps inflation and kneading. What is inflation? Well, think of inflation as you're taking a small reversible circuit and you're adding a lot of redundancy to it. Think of it as adding a lot of complexity fat to the circuit. I'm just adding a lot of fat. And you blow it up in size. So you take a small circuit, add a lot of fat, blow it up in size. How do you add a lot of fat? Well, you take a small size circuit. So you take a sub-circuit, like a sub-circuit in the reversible circuit of size 2, and you replace it with a bigger circuit. Let's say in this case of size 5. And the bigger circuit is functionally equivalent to the input circuit, like the size 2 circuit. And you do this many times over and over and over and over again. And that's how you inflate the circuit. You're adding a lot of fat to the circuit. This is inflation. The second step is kneading. Think of kneading as you've added a lot of fat. So you can obviously take away the fat, right? Like you can obviously very easily reverse the thing down. What kneading tries to do is that it tries to mix a lot of added fat with the actual computation. So that with the hope that after a while it becomes locked and you cannot reverse it. You can think of it as, if you're familiar with complexity theory, adding a lot of fat sort of decreases the complexity of the circuit, and kneading sort of hopes that with some randomization you spread around the added decreased complexity around the circuit, so that at random, if you pick a sub-circuit, it has enough complexity. The way kneading works is that you take, again, a size 5 circuit in this case. So previously, at the inflationary step, we were taking a size 2 circuit. Now you take a size 5 circuit, and you replace it with another functionally equivalent size 5 circuit. When I say functionally equivalent, the input and output of these two circuits are the same. Okay, so that's up, and you do this many, many times with the hope that the circuit becomes locked, which means that you cannot reverse anything that has been done to the circuit. Okay, so if we do these things, if we do inflation, we do kneading, how do we know that obfuscation is really happening? So to measure the effectiveness of obfuscation, we define a very simple metric. And the metric is how correlatable is the obfuscated circuit with the original circuit. Like how correlatable it is. And there could exist multiple heuristics for correlation. And I'll simply stick with two, because at the moment for our experiments, these two suffices. The first one is something called computational flow heat map. And I'll get to it, what it is. And the second one is somewhat simple. It's like reversible circuit optimizer. You can think of it as an analog of Boolean circuit optimizer. We have Boolean circuit optimizers in the world. Think of it as a reversible circuit optimizer. Like you're reversing the, you're trying to optimize the reversible circuit, and that's it. And if you're able to optimize the reversible circuit back to the original circuit, then obviously obfuscation doesn't work. Okay, so we've got these two things. I'll tell you what computational flow heat map is. Okay, so what is computational flow heat map? So computational flow heat map sort of, I wouldn't call it computational flow because it's pretty long. Let's just call it flow heat map for now. So flow heat map sort of builds on a very simple idea. What it says is that you have two circuits of different sizes, because the original circuit that you obfuscate is way smaller in size than the obfuscated circuit. You sort of chunk these two circuits into smaller time slices. And if the state at any time slice of these two circuits, let's just say the first circuit, like you chunk these circuits into 10 time slices, so 1, 2, 3, 4, 5, 6, 7, 9, 10, and if the state of these two circuits, the obfuscated circuit and the original circuit, at time 5, or like time I, whatever I is, if the state is moreover similar, if the states are similar of these two circuits at that time slice, then they're correlatable, which means that you can say that sort of the computational flow on the obfuscated circuit is similar to the computational flow in the original circuit. So that's and computational flow heat map sort of builds on this simple idea. And if the state of the two circuits is similar for many time slices, then they're obviously correlatable. And when I say of state, think of as the Hamming weight, like how many values in the state are 0? So how many values in the state are 1? Think of that as the state of a particular circuit. So you build on this simple idea, and that's it. So you build this heat map. Along this axis is the original circuit, like time slices of the original circuit. Around this axis are the time slices of the obfuscated circuit, and each data element sort of like represents the Hamming distance, like Hamming distance of the distance of the Hamming weight of the states of the two circuits at any timestamp. And if the Hamming weight is if the Hamming distance, if the Hamming distance is somewhere around equal to the half of the wires in the circuit, like the reversible circuit has many wires, if it is equivalent to the half of the wires, then the circuits are not correlatable. But if it is biased, then the circuits are correlatable. So what you should observe in the heat map is that the circuits are not correlatable. You should observe something like this. But if they're correlatable, you should see a straight line. Okay, so you see a very definite straight line when they're correlatable. Okay, so I've told you about what is obfuscation, how do you do it, how do you measure the effectiveness, but the question is does this work? Well, we don't know. We've been running experiments for a while. Our experiments are explicitly designed to get something conclusive. Up till now, we haven't been able to gather some information, but we have some information that we can show. Like, looks like there's something there, but you cannot read it for too long. Like, you should not overread this information. Okay, so the experiment one, what did we do? Well, we sort of ran inflation. We took a 1,000-gate circuit. We sort of added a lot of fat. We inflated it to a 300,000-gate circuit. And then we ran kneading for 500K times. And every time we were doing replacement at the inflationary stage, we were going from 2 to 4. So every inflationary step sort of increases the size by 2. And at kneading, we went from 4 to 4. And the results are that we did not observe any obfuscation. Our circuit optimizer, which is the reversible circuit optimizer, was able to reverse the circuit back to the original circuit. And the correlation sort of like tells you that the circuits are correlated, right? You see a straight line. The two circuits are correlated, the original circuit and the obfuscated circuit. And then we thought that we should try to do something more. So we ran kneading for like 1 million, 5 million, 10 million. Like, it doesn't help. You still see the same thing. But then recently, we sort of did something else. We sort of like took a 256-gate circuit and inflated it very minimally, like very minutely. So we only inflated a 256-gate circuit to 1800-gate circuit, like very minutely. And then we ran kneading for 500K times, and we observed something special. We observed something like this. It's still correlatable, but it's very blurry. And our circuit optimizer found it really hard to optimize it back. It was not able to optimize it back. We are still stuck at 700 gates, probably from last night, and it is not able to go below that. What changed? Well, in this case, nothing changed. The only thing that was changed was that we inflated very minimally. And that's it. Like, we just inflated to 1800 gates instead of inflating to 300K gates. And then we sort of like, we got curious. We sort of, instead of just running for 500K kneading, we ran the minimally inflated circuit for 1 million times. We ran kneading for 1 million times. I'm not sure whether you can observe this, but as you run more kneading, the graph becomes more hazy. Okay? So we don't know whether more kneading would sort of like erase the line. We still haven't observed it, but it's still running. And these results are very recent, honestly. I don't know, like a week back or 1.5, 2 weeks back. Okay, so what is the takeaway? I'm sort of running out of time, so I'll just quickly go through this. So it looks like the key variable is that you need to be running more kneading steps per unit area of the circuit. And inflationary stage only seems to sort of like jumpstart the kneading stage so that the kneading stage can do its work. There are open questions as well. Well, first open question is you need to develop an understanding of, like, we don't understand the inflation and kneading stage that well. We need to develop a better understanding of these things. There's no security proof. So even one day our experiments be like, the obfuscation works, no one would trust us because there's no security proofs. So if you're a researcher in the room, you should sort of like think about these problems. And we need to improve the sampling random circuits. It's like a runtime thing. You don't have to worry much about it. Okay, I think I only have like 30 seconds. So I'm going to
sort of skip a few things. These are like the impractical schemes. And I would sort of like move on to credits. Basically, so I'm just the person who's speaking here. John Philip put in a lot of effort to build the Phantom VM, the RISC-V virtual machine. The local mixing approach is the experiments and all the things that we did was in collaboration with the authors, Ran Kennedy, Claudio, Ododo Andre, Eli Baum, who's a PhD student, Kalari, who wrote the circuit optimizer, and sort of wrote it, which was able to sort of break a off-grid circuit, Alexander, who works at Phantom Zone. And that's it. Right on time.